Chapter 4, Linear Regression. We will now focus our attention on relationships between two quantitative variables. Examples: SAT score versus college GPA, SAT scores are often used as one of the factors to decide who gets into competitive colleges, and if that is going to be the case, then we'd want to make sure that's justified. So we might want to look to see if higher SAT scores are connected with higher college GPAs and vice versa. Another example might be advertising spending versus revenue from sales. If we're going to spend money on ads, we'd like to see that expense is being paid back in extra sales and revenue being brought in that way. So when we look at these relationships, we're going to find that they're often linear in nature, and in fact that's the only kind we're going to look at in this intro stats class. So before we jump in and start looking at those relationships between the variables, we're first going to review linear relationships a little bit by themselves. And that's section 4.1, linear equations in statistics. So in statistics, the way we write a linear equation is y equals b0 plus b1x. And that might look foreign to you. You probably are more used to, coming from an algebra setting, seeing y equals mx plus b as the way that we would write an equation. And just some reminders about what the different things meant there. The m was the slope of the line. The b gave us the y-intercept, which would have been 0, b. And then we had some names for the variables as well. The x we would maybe have called the input variable, and y the output variable. So in some sense all those pieces still need to be over here in this equation, and what makes m the slope is that it's the coefficient of x when y is by itself. Over here we have y by itself and the coefficient of x is b1, so b1 would be our slope in this case. And so b0 would be the y-intercept, 0, b0. So just a quick comment on the difference in the way we write this. X would be considered a predictor, and y is often known as the response, or you could say the prediction. And so when we make an equation of this type in statistics, we're going to use it to make predictions. So we'd plug some predictor in, like maybe SAT score, and the equation would respond with a prediction for the college GPA. But if you think about making predictions, you might want to not only use SAT score as a predictor, but you might also want to mix in something like high school GPA. And this format of the equation allows for that expansion, where we could say y equals b0 plus b1 times x1, the first predictor, plus b2 times x2, the second predictor. Now it turns out we don't cover that in this intro course, but that is what this ends up extending to, and that's the reason they set up this equation in this different format than what we're used to in algebra. So we have to get used to this little bit of a rearrangement, but the slope is still the coefficient of x, and the b is 0 is still the y-intercept coming from the constant term. Alright, so now let's go ahead and review graphing a little bit. They've got an equation here, y equals negative 8 minus 4x, that they want us to graph. And the easiest way to do a graph of a line like this, I think, is to make a chart of x values and y values. And when your equation is solved in such a way that y is by itself, it's usually easiest just to plug in some x's. The algebra strategy would be to plug in maybe 0 because it's easy, and then something on the positive side, something on the negative side, and then see what we get for the y values. So to plug those in, to get those y values, we plug in the x's that were given. So if we plug in that 0, negative 4 times 0 is 0, so we just get the negative 8. So we have 0, negative 8 is our y-intercept. If we plug in the number 2, we get negative 8 minus 4 times 2, which is negative 8 minus 8. The two negatives combine up, we get negative 16. And then if we do the negative 3, we get negative 8 minus 4 times negative 3. And here when we're multiplying, those two negatives are going to make a positive, and we end up with plus 4. So it only takes 2 points to draw a graph of a line, so I did a third one just as a check. And now I'll go ahead and set up a coordinate system and graph this. So I'll draw just kind of the algebra style vertical axis down the middle, horizontal axis down the middle. And the horizontal would be my x-axis, the vertical would be my y. And I'd want to pick a scale that fits these data values. All the x's I pick myself, and I use fairly small numbers, so that allows me to just do a standard numbering where each square is worth 1. And on the vertical, if I tried to do the same thing, I would not be able to fit in the -8 and the -16 on the grid that I've drawn. So I want to use a different type of numbering there. Since all of my y values turned out to be multiples of 4, I think I'd want to number in 4s. And if you just check that, 4, 8, 12, -16, that would fit our biggest value. So it'll be easy to plot in 4s in the sense that all of our y values are multiples of that. And everything will fit nicely on the graph if I do that as well. So I'm going to go ahead and do 1s on the horizontal and 4s on the vertical. And it's not only acceptable but pretty standard to use different scales on your x and y, especially in a stat setting. So now I just want to go through and plot my points. So I have over 0 down to -8, right 2 and down to 16, and left to 3 and down to -16. I'm sorry, up to 4. So up to 4 would be right here. And all three of those do seem to be lining up, so that's a good sign that I've done this correctly. And I'll go ahead and line that up with the ruler and then draw in the line. And then just another quick couple checks on that. The y-intercept was 0, -8, and we did hit that point. And our slope was negative, and we do have a line that goes downward, so you might remember that from algebra. So those are some quick checks to kind of verify that it seems like we're doing things properly. Alright, let's go ahead and give a try to the next one, y equals -1 plus 2x. I'm going to use the same style of making the table. I'll plug in totally different x values this time. Okay, so you might see I plugged in almost the same thing. I just switched the signs on those. You can plug in anything you want there, really. So I could have plugged in the exact same things. I could plug in brand new numbers. I could plug in messy numbers like 3.14, but any three really will do in this kind of algebra context. So plugging those in, I get y equals -1 plus 2 times 0. That cancels out. We just get the -1. Y equals -1 plus 2 times -2. We get a positive from, 2 times -2 is a -4. And then those two negatives add together and we get -5 for that output. And then finally, if I plug the 3 in, I get -1 plus 2 times 3, which is -1 plus 6, or +5. So it looks like I'm getting pretty small x values because I picked them, but I also, just kind of by luck, got pretty small y values also. And I believe with the amount of spaces I have here, that will allow me actually to number in 1s in both directions. So I'll go ahead and do that. So drawing in my axes just down the center, kind of the standard algebra way. And then setting up my scale. It's not enough just to mentally decide I'm going to number in 1s. I need to mark that on there so people can tell what scale I've decided to use. And even though I went in 4s last time on the vertical, I can make a scale that's 1s this time because my biggest and smallest y values are 5s, and I do have 5 grids, so those will fit on. So I'm going to go ahead and plot those. Over 0, down 1, my y-intercept. Left 2, down to 5, and right to 3, up to 5. And I see a couple important things. 1, these are lining up, and 2, I had a positive slope of 2, and I'm getting a line that has an upward path as I move from left to right. So that all seems to be confirming that things are are going well on this line. Alright, just one last quick thought on this before we leave to the next page. If you looked at these and asked yourself the question, which one of these is steeper, I think you might go with this maroon line right here rather than the purple up there, just by the way it looks. But the truth is, this purple line is steeper because the slope is telling me that every time I go over 1, I'm going down 4. And on this one, the slope is 2, so every time I go over 1, I'm going up 2. So when I move over 1, the height changes by 4 here, and only by 2 here. So there's some sense in which even though this one looks steeper, this one is actually twice as steep. Now if that's a little confusing, that might explain to you why algebra teachers will often say that you shouldn't use a different scale on the x and y, because when you do that it does distort the steepness like we saw here. But when you're in the stat setting, you're going to be dealing with numbers most of the time that make it very impractical to do scales that are the same on the x and the y. So we need to get used to the idea that if steepness is important, we'll judge that based on the numerical slope rather than based on the way the graph looks. On the previous page, we talked about the sign of the slope affecting the direction of the line, and I just want to summarize that for you here in this chart. So if the sign of the slope is positive, then the direction of the line will be that it is climbing upward as you travel from left to right. If the sign of the slope is negative, then your line will be decreasing or dropping down. Again, that would be read as you move from left to right. This line's going down, that line's going up. And then finally, if the sign of the slope is 0, then you're going to have a horizontal line, not going upward or downward, but just flat, straight across. Now the one thing that you might think of as missing from this chart would be an undefined slope and a vertical line, which we would talk about in algebra. That's not really of much interest to us in statistics because our big question in regression, or one of the big questions, is about what happens to the y value when the x gets bigger. So here on a positive slope line, we see that if x gets bigger, y gets bigger also. And on a negative, if x gets bigger, then y gets smaller or goes down. And this one's even a fairly interesting question: what happens when the x gets bigger and the answer turns out to be nothing happens to the y? But on a vertical line, the x is not allowed to change, so x is not allowed to be bigger, so that takes away one of our most important questions: what happens to y when x gets bigger? So we're not that interested in that case. More than being interested in slope as just what the line will look like, in a stat class we're very interested in the slope in terms of what does it mean. So if you take the slope m and put it over 1, or you could say b1, either one, I'll use the m because you're probably a little bit more used to that, that would be change in y over change in x. And so when we interpret the slope, what we do is we go from bottom up. Whatever our slope number is, we put that over 1, and then we say if the x value changes by 1, then the y value will change by whatever the slope is. And then because the x is changing by a positive 1, we can refer to it as an increase of just 1 unit. So let's go ahead and try and translate what I'm showing you in the scratch work into kind of a template for interpreting slope. So the meaning of slope is that for each additional unit of the x value, the y value is changed by the slope. So for each additional unit of the x value, the y value is changed by the slope. We say it's an additional unit because we know this is a plus 1 here. We say changed by the slope for the y value because sometimes our m will be negative and this will be a decrease. Sometimes our m will be positive and this will be an increase. So that will vary from application to application. So let's go ahead and take a look at one of those applications right now. The cost of throwing a birthday party at a popular kids' party center is given by the formula C equals 50 plus 10K, where C is the cost in dollars and K is the number of kids. They require a minimum of 10 kids to book a party, and the maximum capacity is 40 kids. Interpret the slope in terms of the application. So the first thing we need to do is figure out which one is the slope. So if I just copy that equation down, C equals 50 plus 10K, then what we want to look for is on the input variable, what is the coefficient? And our input variable here is the number of kids, and its coefficient is 10. So it looks like our slope is 10. And normally, like I showed up above, I would put change in y over change in x. But what the more generic is for that is change in response over change in prediction, or predictor, sorry. And so in this case down here, our predictor is the number of kids and the response is the cost of the party. So the response always goes on top and the input, or the predictor, goes on the denominator. So I'm going to set this up as change in C over change in K, and then I'm going to write down what the slope is. It's this number 10. I want to think of it as a fraction, so I'll put it over 1. And then to interpret it, it's very helpful to know what the units are. So I'm going to put the units on this denominator that go with this variable over here in this denominator. So this 1 I'm going to say is 1 kid. And then this 10 on the top would be the change in C, or cost, and the cost was measured in dollars. This is all just scratch work, but it looks like there's a $10 per kid charge. But you want to be careful because the party doesn't actually cost $10 per kid. You can kind of see that by saying, what if 10 kids came to the party? The cost would be 10 times 10, which is 100, plus 50 is 150. And $150 for 10 kids sounds like $15 a kid, not $10 per kid. So when we interpret this, we want to go from the bottom up, and we want to make sure we use this word additional. So let me try it just over here on the side in words, and then I'll put it to print. So for each additional 1 kid that goes to the party, the cost of the party will increase, because this is positive, by $10. And let's write that out. So for each additional kid that comes to the party, the cost will increase, because it's a positive slope, by whatever the slope is, which is $10. So for each additional kid that comes to the party, the cost will increase by $10. So this doesn't tell us how much the overall cost of the party will be per kid, but let's say we had the party set up and all of a sudden at the last minute 5 extra kids showed up. Then we could say, okay, 5 times 10, that's going to be $50 more for this party than we originally thought. Okay, continuing on with the application about the cost of a child's birthday party, let's go ahead and sketch the graph of the line that they gave us. So just like I showed you before, I think the easiest way to make such a graph is to go ahead and make a table. Normally I would do X and Y, but if I bring in that problem we were working on, we can see that our variables were not X and Y. Our input variable was K, and the output variable was C. And then I'm going to put in different values of K, but I'm not going to do 0, 2, and -3 like we did earlier. I need to plug in numbers that make sense for this application. And a lot of times what it's good to do is think about what makes sense as a minimum and a maximum cost. And in this case, they've actually set that up for us. There's a minimum of 10 kids to book a party, and the maximum capacity of the room is 40. When you know what the extreme values are, you should definitely use those as inputs. And then if you want to do another one, throw maybe 20 kids in there, just have a third point for a check, you could do that as well. If you don't know what the min and the max are like we were given here, then I think you just want to make a reasonable guess at what a min and max would be and use those in your chart. And then next, I want to go ahead and go to the calculator and start calculating the costs of these. So let me go to my home screen here, and I just want to plug into my equation C equals 50 plus 10K. So I have 50 plus 10 times 10. This is the one we did in our head a little earlier. So that'd be $150 if 10 kids come. 50 plus 10 times 20. Actually, we'll do them in order here. The 40. That would be $450 for the party if 40 kids come. And then finally, 50 plus 10 times 20. It would be $250 if 20 kids come. So let me go ahead and fill in all of those to the chart. So the $10 party would be $150 cost, 40 kids, $450, 20 kids, $250. And now I want to go ahead and graph those. And since we're dealing with an application instead of just an algebra equation, I think that it makes sense to draw our axes on the far left and the very bottom instead of through the middle. And that is often the case for applications, as long as it's the case that there's no negatives. And we can't have a negative amount of kids come to the party, and we're not going to have a negative cost for that party either. So in this case, left and bottom do make sense. And then the input will be our kids, and the output will be the cost. It might even be good to label that as number of kids and cost, and maybe even remind ourselves that the units there are dollars. And then we want to think about the scale. So on the cost, we need to make it up to 450, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares for that. So if I take my max cost of 450 divided by 10 squares, it says I could number in 45s, but we want to round that up to something nice, so I think I'll round that up to 50, a number in 50s, or use a scale of 50s. I'll actually number every other one, so it looks like I'm numbering in hundreds, but the scale is indeed 50 per square. And that'll put 450 up near the top, which is good. And then as I go across the horizontal, I want to make it to 40. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 squares. And so if I need to make it to 40 with 20 squares, that feels like that would be numbering in 2s. I'll show you the math on that. So we want to make it to 40. We have 20 squares to do that in, so numbering in 2s will get us there. So 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, 2, 4, 6, 8, 30, and 2, 4, 6, 8, 40. And then I can just go ahead and throw these points onto the picture. So over 10, up 150, so that'd be right here. And then over to 40 is up to 450. And over to 20 is up to 250. So hopefully those line up. It looks like they're lining up pretty good. We'll see that better when the ruler comes in. It looks like they do match up, so I'll line them up, drawing the line. And this isn't a huge deal, but I do want to point something out, which is that when I draw this line, I actually stopped at 40 and stopped at 10 rather than extending it in both directions. Again, not a huge deal, but the problem did say there's a minimum of 10 kids and a maximum of 40, so I don't think we should extend the line out to beyond 40 or before 10, since that doesn't really apply to this situation. I'm going to finish up this section by looking at an example where our data is not perfectly linear. Let's go ahead and read through that. Samples are taken every year to estimate the percentage of adults who smoke cigarettes in the U.S. The table below lists the year and percentage for 10 such samples. The scatter plot, together with a prediction line, is provided below the data set. So they've given us the years 1985 through 1998. You might notice the years are split on two lines, but that all still is just one variable. And then the percentage of smokers going from 45.4 in 1985 down to 32.4 in 1998. So they said the scatter plot is provided, and so we can see that over here. And as you can see, the numbers are decreasing for the percentage over time. You can see that trend in the scatter plot as well. And in the scatter plot, we also get that additional information that that pattern looks like it's a bit linear. And then they've given us a prediction equation down here, and they've graphed that equation for us already. And just a quick note about prediction equations. It's common that instead of saying y equals, we'll say y hat equals, as we like to differentiate between a real y value from a piece of data like this 38.9 versus a prediction we might make, which we'll call a y hat. So let's go ahead and make use of this. So use the prediction equation provided to estimate the percentage of smokers in the U.S. in 1996. So to figure that out, we just want to substitute this 1996, which is a year, so an x value, into our equation. So we would have y hat equals 2113.11 minus 1.042 times, and then we'll substitute in the year 1996, And then of course that's a little bit messy, so we'll want to go to the calculator on that. So let's see. We have 2113.11 minus 1.042 times 1996. And when I do that, I get 33.278. And then just keeping in mind that this is the percentage of smokers, so I'd say that's 33.278%. And that would be my answer. So when they give an equation like that, we can just substitute in to get our prediction, and we designate our predicted value with a y-hat. And then next, they ask us to find the prediction error, or residual, for the ordered pair 1998 32.4. When you want to do prediction error, what we always do, we'll label that with a little e, and that's always y minus y hat, where y would be the y-coordinate of an actual piece of data that we're interested in the error for, and y hat would be the prediction or predicted value from the equation. So in this case, we know that the y value of the data we're provided is this 32.4. What we don't know is what the predicted value for 1998 would be, but we can get that by doing the same thing we did up here, just changing this 1996 to a 1998. And since that is just a change on that calculation, I would bring in the calculator there. I would just hit the second and the enter button to bring that calculation up, and I would just change that 1996 to 1998. Press enter, we get that new prediction, which I'll write down, 31.194. And then our residual, or prediction error, is that difference between that 32.4 minus our predicted value, 31.194, and we get 1.206. And again, that's percentage points. So I would say our error for the 1998 value was 1.206%, because the actual value is 32.4%, and our prediction equation gave us 31.194%. And then finally, interpret the slope of the line in terms of the application. So first of all, we want to pick out the slope. The slope is going to be our coefficient of x, including the sign, and so that would be negative 1.042, and that would be the change in y hat over change in x, change in output over change in input. That would be negative 1.042, and I would make that a fraction by putting it over 1. And then I'd want to write units on that. So the top was change in y hat, which was an output, and the output was percentage of smokers, so I'll just put percent on there as a reminder for me. And the denominator of 1 was the change in x, and x was our input, which was the years, so I'll put that on there. And then when I interpret slope, I usually go from the bottom up. So I'd say for each additional year that goes by, the percentage of smokers in the U.S. is decreasing by about 1.042%. Let's go ahead and write that out. So for each additional year that goes by, the percentage of smokers in the U.S. would decrease by about 1.042%. Alright, so again, you want to do the slope interpretations from the bottom up. So for each additional year that goes by, the percentage of smokers in the U.S. will decrease by about 1.042%. And that's it for section 4.1.